Yes, I'll be very happy to give you a presentation. And when I was thinking about what to present, so it's essentially a journey that will describe the variety of projects that I conducted. And we start with, looking at what's currently driving us, right? So, and if we look at in our field, data management, big data, we see that data management and big data clearly together with machine learning has a profound impact both on data science and artificial intelligence. So we are in a very important space in the data management community. And that again really alters both the sciences and the humanities on the one hand and industry on the other side. And I will illustrate this with two examples. And the first one is in the sciences. So in the sciences, what we can see that is, and that's a term that has been dubbed by the late Jim Gray, the fourth paradigm, that we really can observe a paradigm shift that has happened in the last decade and is really informed upon and is really advanced by our data management technologies. And that is the fourth paradigm means that in contrast to the first paradigm that millennia ago, we had empirical sciences that observe and describe natural phenomena like Aristoteles describing the basic elements, right? Then we had in the last centuries, theoretical science that was essentially observing, building models that generalize, like the apple falls from the tree, and then you derive, or Newton derived, force equals mass times acceleration, and then gravity, right, was coming out of that. And then the last decades, again, there was a paradigm shift in that the sciences have moved into computational sciences, where large supercomputers, high performance computing, used complex, usually differential equations to build and simulate large phenomena, and that allowed us to conduct weather forecasts or climate research or dynamical models, right? But in the last, more or less decade or so, we have seen another shift, and that has happened because more and more data is available that's generated through measurements and simulation, where the data exploration takes place through software. And the information is really processed using data management techniques, statistical techniques, and even sometimes more advanced correlation finding through machine learning or so. So that's really a paradigm shift in the sciences. And in the same way, we have seen such a shift in industry. And in industry, probably you have often heard the term that people have talked about in the context of big data, which is data is the new gold or data is the new oil, which I actually totally disagree with. I think this is not the right coinage of the term, because data is not a resource, right? Data, in contrast to like oil or gold, is not a resource, because a resource is something you put in the production process, it's being consumed and it's gone, right? Whereas data is more like a production factor in economic theory, and the production factors are usually labor and capital, right? And soil, because you can grow something out of the soil. And that's why I like to talk about data more as the new soil. And what that really means is, you can see this analogy here that, like the soil that you have to work and treat with fertilizer to have something grow that you exploit, that you then can collect. With data, you have to do a similar thing. Data is something that you have to prepare, you have to enrich it, you have to process it in order to derive insight. And it's also a loop in the sense that once you have produced something, the soil is not gone, it's still there, right? And the same way the data is gone and you can derive something else, you can produce something else. And so that means data has a much more crucial role than just being a resource. And that means, again, from a data management research community perspective, we have to look at data management as a whole and have to provide the means for managing those vast amount of data, running machine learning algorithms on them, which is really what allows a lot of the exploitation and treatment on them now. So this is really, again, a paradigm shift, but our role as data management community is huge in that space. And in this context, of course, we all, and you all know about that, I'm very sure, those terms of big data with those 3 V's of volume, velocity, and variety, right? But what we really see in this world is, and we have seen this over the last years, that machine learning and data management are coming together. Machine learning brings more complex algorithms, and data management brings scalability. And the key observation here is that, of course, in the data management community, we had solved the problem of scaling to huge amount of data at high velocity, also integrate the data quite well, as long as we were operating with relational algebra, right? Because as long as we operate in relational algebra, we have a certain set of very well-defined operators with selection, projection, the Cartesian product, and of course the derived join operation, and union and intersection and difference, right? That allow us to process and of course derive operators a huge amount of data inside questions, but not so much the new algorithms that come about with machine learning. And the interesting thing is what the difference here is. Of course, there's a difference in the data type that we often operate now in matrices in machine learning. But a key difference from the data processing perspective is that machine learning algorithms tend to be iterative in nature, whereas relational operations usually read the data at most 3 times, right? If you have to do sorting, you have to read them 3 times. As we always say, right, complexity of sorting with two-phase multiple merge sort, it's not really n log n anymore, but you just read, write, and read the data with proper in-memory sorting if you count IOs. So it's still, all the operations in practice are really linear, right? As long as we are talking about reasonable amounts of data and have enough cache, and reasonable amounts would be petabytes or more, right? So we can manage that all in linear operations. However, if we talk about machine learning, then we iterate and we get a different complexity. And this is where things suddenly start to break. And the other part where things start to break is that the data doesn't necessarily come in the relational data types. So you have to conduct ETL or ELT. So you have to apply essentially user-defined functions on the data to create the schema while you start to process it. And those are where our existing systems break and where we have to look into new systems. So if we look at the data science process, right, that is really derived for those machine learning systems, that means we first have to extract and integrate information, which is usually applying user-defined functions on the data in addition to relational operators, and that at scale. And then we have to analyze and build models. And this analysis model building phase usually involves iterations and maybe even different representations of the data in matrices or other forms that operate on linear algebra more than relational algebra. And of course, we have a loop here in the sense that in the same way as we talked about before with the soil, right? Once you have the model, you may actually find that some pieces are missing and you need to integrate new pieces into the model and so on. So this is what a human has to do. And if we now look at the role of the data management community in this process is, the way I look at it, that the data management community has 2 major aspects here. So we have to look at, on the one hand, if we want to map this to computer architecture, we have to specify such a data analysis program, right? It has this workflow from extraction to model building has to be specified and then mapped onto a computing infrastructure to run on massive heterogeneous data sets and streams. And it has to be then executed by the hardware efficiently. And the way to do that, that we have 2 problems. We have on the one hand, during specification time, the human latency, which really arises from the fact that a human has to code this workflow and in a form that can be processed by the machine. And then we have the technical latency because, of course, we're operating on large data sets. We need to make sure that those large data sets are processed efficiently. And that entails, of course, mapping it into large compute clusters and making good use of all the hardware, worrying about technical, physical operations on the data and so on. And from a community perspective, we have dealt with that, in particular, very successfully with relational databases, with declarative languages where we specify what but not how, and we have query optimizers, right? And of course, Emmanuel also teaches that quite a bit and has done a lot of work in that space as well. So we're talking about having query optimizers and looking at automatic optimization that takes such a declarative specification and maps it into onto the underlying computing infrastructure. However, as said, that changes, of course, to some degree if we are not talking about relational algebra anymore. Now, with respect to the technical latency, we have to now look at, once we have such a specified program, that we efficiently parallelize, distribute on the large clusters, do smart caching, and have proper algorithms for both in-memory and out-of-core execution. And this is really how the data management community is addressing this rather complex workflow. And in this context, we see, because we have not really achieved that. So in my opinion, we have really gone quite a step back. When all the systems came about after relational database systems, we have, systems like Hadoop, Spark, Flink, and whatever, right? They all put a really excessive demand on those data scientists, in the sense that data scientists, on the one hand, need to know the algorithms and methods, which involves machine learning, statistics, and data analysis. So you find some buzzwords here on the left side of the slide. And at the same time, they have to deal with the technologies and the systems that are underlying in order to make this scale. But on top of that, if we talk about big data, high velocity data, the data scientists have to have domain knowledge. And this is too complex. And as said, the key thing that made database systems, in my opinion, so successful and really enabled this billion-dollar market was the fact that we were able to relieve the domain area experts from the technologies in the black circle, because pretty much all of that we were able to automate in relational database systems by having the query optimizer, having intelligent algorithms, having relational algebra, and so on. And the need that we have now in this emerging world of artificial intelligence and big data is machine learning, to bring this back to our systems, because right now we have this really zoo of technologies that Matt Turk is assembling every year. This is an older slide I just realized, but the 2022 slide would look even worse in the sense that we have a huge amount of different technologies that those experts in big data and AI should master in order to solve specific problems that involve certain data types, like maybe text or graph data or some other forms of relational data that all have to be brought together using certain algorithms in a certain scale. And in order to really do that, we need to help with the automation by reducing both the human latency and the technical latency. Particularly human latency is a big challenge. And I want to go back in history a bit and just look back at what we did in the context of first the Stratosphere project that led to Apache Flink, where we started sort of this vision, which is we want to combine general purpose programming with database execution. So trying to combine the best of both worlds, if you wish. And back then, the key was MapReduce technology, which I think still is quite useful in the sense that MapReduce technology is, of course, popular from functional programming languages and then popularized by the paper by Jeff Dean and Genovat that was essentially mapping this to a scalable execution framework, because it allowed, on the one hand, scalability for thousands or tens of thousands of computing nodes, while at the same time not prescribing a schema. And that was a big advantage, in my opinion, that you did not have to define the schema. That's also what enables data lakes today. You can have user-defined functions that will impose a schema during analysis time, and you can effectively have schema on read and also arbitrarily complex data types because of that. And this is very powerful. At the same time, one lost a lot of things that we're still losing in today's systems, even in systems like TensorFlow or so, which is having query optimizers that would allow us to automatically map this into a clean execution framework like we have in database systems where you have relational algebra, declarativity, and of course with all of that mapping the query optimizer that results also in robust execution both for small data sets in core or out of core for large data sets. And so those two worlds, combine them and at the same time add some new features. And the new features are iterations. So adding, in this case, the capabilities of dealing with iterative algorithms and also some more advanced data flows and native streaming. Native streaming means dealing with data at line rate when it comes in and actually for each of those data items that come in being able to act. And that means usually instead of having batch data, you have to discretize your data, right? Because you can operate only in a discretized version of the data. Discretization usually means we define a window over the data, maybe time-based windows or other types of windows. And so those were the key ideas, and that led, and Emmanuel already said that also in the beginning, that led to Apache Flink system that we developed in my group. That's an open source stream processing framework that essentially deals with both bounded and unbounded data, which means both batched data and the unbounded continuous streams that are discretized. And one key thing with streaming is that we have to deal with time. And time is one thing that usually in data management we don't like, or in general, we do not like concepts like order, because order effectively limits the ways we can parallelize things, right? When you have something in a certain order, you cannot arbitrarily parallelize things. And so you have to be careful in how you deal with event time semantics, and at the same time, do this in a distributed fashion, right? Having, in Flink, we do this in an environment where you have thousands of nodes with good throughput and latency, and at the same time allow for those stateful computations that you have either in Windows or also in iterations. And I'll talk about iterations a little bit more later. You need to have deal with state. And state is also an issue in the sense, of course, you have to worry, if you have thousands of computers, you have to worry about fault tolerance, and you have to worry about, of course, also efficient processing of state in a distributed way. So with respect to windowing, it's also important to point out that, of course, systems that are following more a batch-based paradigm, they can also conduct streaming as long as you look at windows that are called count-based windows. Count-based windows means windows that have the last n records, right? And choose your n to an arbitrary size, which would traditionally be your batch size. Then you can have pretty much any batch system simulate a streaming system. The problem is, of course, that if you want to move into near real-time or real-time data processing, you usually don't look for count-based windows, but you discretize your data stream in a different way. So, of course, there may be time or session windows, but in particular, windows like if you have a geo data processing system, you might have people walking on streets, and if somebody enters a certain street, that might be a window, right? And so people moving from one street to another street would then create essentially an admission or an injection of a window. And in Flink, because Flink is a true streaming system, so it doesn't batch the data, you can implement those kinds of windows, and you can have arbitrary windows by just defining the window admission and then also the window closure policies. And now, just to describe what that really means with respect to data processing, so in Flink, you have what we would call a declarative data analysis program. Also, one should also be pointing out that declarativity is something in the eye of the beholder, because declarativity always means it's a higher level of abstraction. You abstract a certain level away from the hardware. And of course, in some cases, that could mean, in an ideal world, declarativity means just do what I want, right? And you don't say anything else. If you say the computer, do what I want, then the computer will produce your result. But this may be a too high level of abstraction. So you have to make it a bit more concrete in your steps, right? So, and in this case, what declarativity means, it's even one level below domain-specific languages, because you could also say, of course, domain-specific languages, which, for genome analysis or so would be useful. They provide declarativity. But we are looking, if we're building a system, we are looking for a declarative language that is still generic enough to, on top of that, build domain-specific languages for various domains. So that means you still have to have some general features in that language, right? So that's important. And in Flink, we have in this way, declarative analysis program. And declarative here means we have various ways of mapping it towards a physical execution. And then Flink has just the same way as you would have that in a traditional database system. You have an algebraic model and a cost model, so that the system automatically can parallelize and adapt to the hardware. The difference to a traditional relational database system here is that in Flink, the algebraic model is not relational algebra. It actually is an algebra on second-order functions. So there's a certain set of second-order functions, and those functions are functions like cross, co-group, but also map and reduce. So there's two functions that are, and we call those functions actually parallelization patterns, in the sense that each of those functions on the one hand, prescribes how you would parallelize the computations on the inputs. And on the other hand, they, of course, have a very specific semantics that allows you to construct essentially operations on relational algebra, but also iterations as we need them for machine learning. And the two functions that require a single input and conduct either a record at a time parallel processing of a UDF on that. The two second-order functions are map, which we know already from the reduce model, and also reduce, which operates on a group. So it's a record at a time, group at a time UDF application, right? But those two functions are not enough in order to enable processing of like relational algebra and also parallelize and automate that. And this was also one of the flaws of the MapReduce model. So in order to do that, you need actually functions that have multiple inputs. So you need a function like a map or a reduce, but with more than a single input. And those functions are cross and co-groups. So cross essentially could think of a Cartesian product where on multiple inputs, for each of those input, a UDF is applied. And co-group is, if you wish, a two-dimensional reduce. So if you have those functions, you can build everything that relational algebra has, but at the same time, the beauty is you do this in a more declarative way, so you can optimize across it. And then in order to deal with the iterations, you need a third order function, which is a fixed point iterator on top of that. And I'll get into iterations a bit more later. But essentially, what happens then is you have a cost model, and out of this cost model, you build a data flow graph, which is again very similar to what you would do in relational database systems. The only difference is, again, we are talking about the second order functions, but the beauty is, so we had some papers in 2014 and later at VLDB that also show that you can, by doing some simple static code analysis, meaning I just look at what the first order function, which is an argument to the second order function, what kind of parts of a record it changes or reads, which is almost like similar to what you do in transaction analysis when you do read-write set analysis for transactions, right? So, but just by doing that for the UDFs using static code analysis, you can determine properties when you can commute or distribute some functions into others. So that means you get the usual degrees of freedom that we get in relational algebra from the laws of commutativity, distributivity, and associativity. And you get those by static code analysis. And then you can, for instance, push a map through a reduce or through a co-group or something, and you find rules for when you can do that. And the funny thing about that is if you do the static code analysis, then you can, without even knowing that you are performing a selection, because a selection is essentially a map with an if, right? Inside the first order function, you can actually do selection pushdown, or you can do things like projection pushdown. You can do join reordering, and you can do even early grouping, lazy grouping. So a lot of those optimizations that we know from relational algebra that a relational query optimizer would do, we can also do in such a system by having this first step of the static code analysis and then applying that. And this is really all that happens at specification time. And this is how one can, going back to my initial slide about the human and the technical latency, right? This is how we can reduce the human latency, because now the programmer doesn't have to worry about those kind of decisions about which types of physical operators to use, but also in which order them to use. So that doesn't have to happen anymore. This is really the system can decide. And at runtime, the system then, of course, has to have the typical distributed system setup with coordinator and workers, where the coordinator takes care of distribution of operators and has to do monitoring with respect to ensuring fault tolerance and resource management on the one hand. And on the other hand, the workers have to provide the means for memory management, for out-of-core algorithms, data stream processing, and in particular also for state management. So this is essentially Flink. And I don't think here in the group I have to talk a lot about the impact of automatic optimization. I think it's clear if we have such a declarative program, we can the optimizer can decide execution order, parallelization strategies, in-core versus out-of-core, physical implementations, materialization strategies. And this means that the same program can run on the laptop without any single change. We can run it on a big cluster. The execution is very different, and we can run it much later after data or the environment has changed, and we don't have to change a single line of code, and it still will run and run efficiently. And this is really something that currently, if we talk about big data production pipelines, right, often there's a lot of hand tuning required. So this is really where the reduction of human latency and technical latency comes into play. And this is just a very small example of why optimization is needed. This is a visualization of one of those data flow graphs that you see here with those higher order functions. And of course, one wouldn't want to decide the order of those boxes and also the gray boxes here, which are really how in this distributed setup, when does one do communication via in-memory local forward or network partitioned or some broadcast network operations, right? All of this, the system can decide. And with that, I want to talk about another important part, which is iterations in data flows, which really is what we need for machine learning algorithms, right? This is an important addition to this model, because there's two fundamentally different ways of how to iterate. So the first one is we can iterate by looping, which means essentially a loop, right? Or iteration is really a while loop, you can say. And inside this while loop, I have a function that I apply on a large data set. And I call this function a step function. So essentially, you could say a loop is while some condition executes step function, while some condition holds. And the traditional way in a big data system, how to execute those loops is we have an external driver, the client, that will execute the loop and check the termination condition. And then the step function is run inside this massively parallel framework and executed in parallel. But the problem is that then we check the termination condition and the driver issues that again. And you do this, it doesn't matter, like in Spark, for instance, do it like that. The driver is essentially Java and or the JVM, and then the execution, the massively parallel execution happens inside the Spark framework, or in Hadoop or so it would be the same, right? But the problem with that is you do not really know that you're executing an iteration, right? So the driver is outside of the domain of the optimizer. And you can still do some tricks here and optimize some things, because obviously if you have data in memory already, you don't have to recompute it, right? So you can reuse that. But it's fundamentally different from the second approach, which is really making the iteration a first-class citizen by having feedback edges, so that you inside the step function do some computations, and then you have in this data flow when you have this partial solution, you have a replace edge that will check the fixed point. If it's not met yet, you go back to the partial solution. And if you do it that way, then the data flow is explicit, and you can play much more tricks with optimizations. And some of those tricks are already quite well known, in particular in the compiler community. But of course, you can only do them if your data flow is explicit. So what you can do, that's what any good C compiler also would do anyways, right? If I know I execute an iteration, I can push loop invariant work out of the loop. I can cache loop invariant data, and I can also maintain the state as an index. And this allows, for very fast iterations. And this is also some work that we did that was factorizing a matrix, in this case with Netflix scale or Spotify scale, 28 billion ratings. And back then when we did that, this was actually a record to do it that way. And this is, of course, one trick you can play, but there is more. Because if I know that I have iterations, then I also have the state, which is really the type of computation that has happened within the step function that you do not want to lose when you go into the next iteration of the step function, right? And you don't have to lose it when you know that you're executing iteration, so you can operate on that. And you can deal with that state more efficiently, and you can exploit what are called sparse computational dependencies. So what that really means is, so I'll explain this here more by an example. There's two fundamentally different types of iterations, namely what I call bulk iterations, and the other ones are which I call delta iterations, and we also know them in the context of data log, or so in the context of semi-naive evaluation. And what this really entails is, let's look at, for instance, if I was to compute a transitive closure on a graph. And let's assume the graph has three edges. The edges would be AB with the first edge, BC is the second edge, and CD is the third edge. So if I would compute this transitive closure, I would say in my first iteration, if I would do this as a Warshall algorithm, I would represent everything as a matrix, and I have this cubed complexity to compute it. And every single time I would have to look at every single element in the matrix. Now, this is clear. We can still be smart about it with loop invariant work and so on, but it's a bulk iteration, similar to what a table scan would be on a relational database. I have to look at all of the data in each iteration. The interesting thing, though, is that in this graph, and it's true for many graph algorithms, I have what we would call sparse computational dependencies, because not everything is connected to everything. Like in the example graph that I have given, I could do the computation much more efficiently. What I could do is, I could say in my first set of iterations, I notice AB and BC are in the graph. So one of my outputs, of my new found transitive outputs, would be AC. And similar, since BC and CD are in the input, BD would be in the output. So that means I have two new outputs in this first iteration, which is AC and BD. Now, interestingly, in the next step, because I have those sparse computational dependencies, I only have to look at this new delta that I have computed, which is this AC and BD, and compare that to my original data. And then as a new output, I would compute AD as a new output. And then I'm done, because the next time I would not have a new output. And so here the iteration would be really until there is no new delta added. And that's how I can compute this. And essentially this means I have to split my computation into a work set, the data and the delta set, the new stuff that's being newly added, and iterate over both the work set and the delta set. So in the compilers, it's for that reason also called work set iterations. In database systems, we call it delta iterations in the context of data log. But the interesting thing is you can only do that if you have, as a first-class citizen, an iteration construct in your data flow system, right? And it has a drastic effect. So this is an example. Now, this is computing connected components, which is an algorithm that is similar to transitive closure, and it's a key component for many graph analysis algorithms. And what you can see here is, in the first iteration, I would have to look at everything in the graph, all those edges, which in this case would be in the order of 40 million. And the interesting thing is, if I don't know that I'm executing an iteration, and if I don't know that I can have this incrementalized version of delta iterations, then in each new iteration step, I would again have to look at those 40 million edges. If I have if I use the delta iteration, then and I only look at the new output, then in this case, this is now of course a specific graph, but in this example, you can see that, and it's a representative one though, that the number of iterations goes down quite. The number of items in each iteration goes down quite drastically. And this, of course, makes it much more efficient to compute those iterations. And those are important for also many machine learning training algorithms. So this allows for really very fast graph analysis. And what you can see here is, for instance, if I run 30 iterations on, in this case, it was Hadoop that we did here, that would last a certain amount of time to be computed, almost an hour. If you do this in Flink, because of some optimizations and so on in the bulk mode, it would be in the order of below 10 minutes. And if you do the 61 iterations, which is really when the fixed point is reached, it would be roughly double the time. But if you do delta iterations, the first 30 iterations are much faster, and the last 31 iterations hardly cost you anything. So you can have really very efficient iteration processing that's comparable to dedicated graph analysis systems, which of course implement those kinds of algorithms. But the beauty here is, because you have a full-fledged second-order functional programming system, you can actually mix and match that with ETL style and graph analysis in a single program. And this, of course, if you combine all of that together, then you get lower latency and higher throughput, in particular for streaming applications. And what happened is, Iman already mentioned, so we got some actually also awards for some of our work here, which is we got a best paper award. This was in this context for compressing data streams visualization. Also, ACM Sigma Research highlight for our optimization of iterative programs. And then with respect to dealing with data streams where you have multiple streams where you can share results, how can you reduce latency? So we got a best paper with EBT. And just most recently, we actually had another best paper that was again on the optimization of iterative programs at ICD. And in this context, Flink is heavily used. So we created an open source system, and then there was a lot of traction from companies. So the largest user is Alibaba, probably, that is running it on huge clusters and process millions of events per second. King is running also billions of events daily and maintains large states. King is an online game company that does in-game analytics. Bouygues Telco is a telecom company in France that runs 10 billion events, so 2 terabytes daily. And overall, and this is, I think, also a nice story about the system, that it started with 2 PhD students in my group, and then a third PhD student from the distributed systems group, and then we were able to build a community, first in Berlin, then there were some people from KTH, and afterwards some companies, and then overall. And by now, we have, in the context of Flink, many hundred contributors that really contribute code. And we have a large community of people on meetups that are meeting regularly. And there's a good amount of Flink users that include major companies, including Uber, and also in China, Tencent, or of course Alibaba I mentioned already, but also Lyft, and Google made it as part of the Google Cloud data flow, and Amazon is also using it. So it has been quite a success story, and it plugs and plays with the entire ecosystem. And the key thing is indeed, and that's why I'm telling the story here today, in particular for you as master and PhD students here in the seminar, because it just takes 2 or 3 students, right? And you can, over time, you can do excellent research, and then which is really the basic research timeline that we had here. After that, we moved into this time of applied research, where really we were engaging with the community, engaging with first customers. Then there's also some entrepreneurial activity that can happen by founding a startup. And then there was with our respect to community building, we started to have conferences dedicated to Flink, and then in the end there was even a successful exit for the startup. But the beauty is it happens from the university, and it can happen with just a couple of people, and you can create such a system. And it will be great to see many more repeating those kinds of stories. So with that, I want to actually switch gears a bit. But first, Emmanuel, maybe a question: how much time do I still have?
Can you hear me? So frankly, I mean, so in principle, I mean, at least until like 2:15, if you want. So.
Okay, very good. Okay, very good. Excellent. Then I'll continue with this part of the presentation, which is I want to now change the topic a little bit, and I will talk to you about what we can learn from Roman generals about big data. And this is a story about 2 Roman generals, Marcus Pessimus and Gaius Optimus. And what can they teach us about large-scale data mining? So what you see, so those 2 generals, they had armies or legions that were back then in Germany, because you have to remember this is a map of parts of the Roman Empire back then. And back then, in Germany, there were essentially barbarians. And the Romans would regularly have to send some legions to clean up the mess and deal with the problems at the borders. And so they had those 2 legions there. And now what happened is that the legions, as said, led by Marcus Pessius and Gaius Optimus, were ordered by Julius Caesar to go back to Rome, the center of the universe back then. And now the challenge was, how would they efficiently get back to Rome? Because the problem is, there's those barbarians. There's the German barbarians that might attack them. And if they get attacked, they might lose some troops. They might be slowed down. So how can you do that efficiently and avoid those kinds of problems? And there were 2 strategies. So there was the first strategy that essentially Pessimus employed. So what Pessimus said, okay, what I will do is I will march every day towards Rome. So I will follow, there's those Roman roads, the Roman road network. And what he would do is he would march. In the evening, he would build a fortified camp. If then at night the barbarians attack, he would deal with the attack. and maybe even leave the camp to chase them and then go back to the camps, rest, and the next day keep marching. And here in the corner, you see one of those camps, Roman camps from the corresponding subject matter literature. And you can already see that building such a camp requires some effort, right? You have to fell trees, you have to obviously create those moats. So it's not for free, right? But of course, they keep you safe. Now, Optimus had a very different strategy. So Optimus was saying, okay, you know what? I don't really need any camps. What I will do is, because I have a legion and the barbarians are few. So whenever I see barbarians, I have my scouts, I will chase the barbarians away. So I will leave the Roman road that I'm walking on. So here you see an example of one of those Roman roads. But I will leave the Roman road. I will chase the barbarian through the forest. And then, of course, I'm off the Roman road, but it's not a problem because I will wander around until I find the Roman road again. And as soon as I find the Roman road, I will continue that road again to Rome. So that means I don't have to stop. I don't have to build camps. I will actually just scare them away. And in this way, I should be fine as well. And here's a question for you now. And the question is, why does this strategy even work? There is a fundamental assumption in this strategy. So why does this strategy even get you to Rome? There's a fundamental underlying assumption that Optimus knows that ensures that in this situation he will get to Rome with the strategy. Does anybody have a thought?
Anyone?
Just a random guess. Is it kind of like the stochastic gradient design? So like when you wander around, you're likely to have a high probability that you will get the next Roman road, and then if you follow that road in the right, that will be in the right direction, and eventually you'll get there.
Very good, absolutely correct. That's the assumption. So the assumption is you will find the Roman road, and more importantly, it doesn't matter if you turn left or right. It will get you to Rome, right? So that's the assumption. So in the end, the assumption is really all roads lead to Rome. And of course, we know that that's true, right? And historically speaking, all roads lead to Rome. So that means it's a good strategy to go because it doesn't matter if you turn left or right, eventually you'll be in Rome. But that's a key assumption, and that has to hold. Otherwise, there would be a danger for Optimus not to arrive in Rome. So if it's true that all roads lead to Rome, then there's the next question for you. And that question is, who will be faster in Rome, Optimus or Pessimus? Any thoughts?
Anyone? $50-50 chance.
This stochastic.
Huh?
No, nothing.
No.
No.
I think it like depends on how frequently the barbarians attack and things like that.
Very good answer. And the correct answer is pretty much for everything is it depends, right? So this is what my former mentor Guy Lohmann told me always. That's the correct answer to pretty much everything is it depends. And you're absolutely right. It depends in particular on the frequency of barbarian attacks, because if we have a large amount of attacks, then it's clear that Optimus will constantly leave the road, running around and chasing barbarians, and will take forever to come to Rome, or in worst case might not even ever get to Rome, right? Because he's constantly just chasing barbarians. So if there are a huge amount of attacks, then Optimus' strategy is a problem. And in that case, of course, the strategy of Pessimus, which constantly moves forward, has a high overhead building the camps, but constantly moves forward, will actually make sure that he arrives in Rome faster. However, if we assume that there is very few attacks, then who will be faster in Rome? Then I think it's clear to say, if we don't have a lot of attacks, it's clear that Optimus will arrive in Rome more quickly. And so now you probably all wonder, what does that have to do with big data, right? What does that have to do with efficient data management? And actually the answer is a lot. What we have been talking about here is we have been talking about fault tolerance for iterative algorithms. And so what we are doing is, so we have an iterative algorithm, which I said is the core foundation for many machine learning applications. And those iterative algorithms, they are a while loop with a step function that's set inside, right? And the step function processes in some large state and does some execution. And this is exactly what we are doing by moving to Rome. We are executing an iterative algorithm. The step function each day is one iteration, and in each day we are executing our step function, which is about getting us closer to Rome. So we're talking about a fixed point algorithm. We're trying to get to Rome, which is the fixed point. And each day we are moving forward. And we are talking about fault tolerance here in the sense that we have barbarian attacks. And the barbarian attack is a system crash. So that means we're having this parallel distributed computation. And when barbarians attack, that means we lose some part of our computation. And now there is the common way of assuring fault tolerance, and this is the way that you would usually employ in systems like Hadoop or Spark and so on, is pessimistic recovery. Pessimistic recovery means checkpointing. That means building a fort, building one of those fortified camps, which is writing what your intermediate state that you have already computed, write that to stable storage. And then when you have a barbarian attack, when you have a machine failure, you will restart from such a checkpoint in the case of failure. And the interesting thing, or the problem is that if you don't have a lot of attacks, as we said, if you don't have a lot of system failures, this is a very high price to pay. It's a very high overhead. And I had one of my students look into this, and we measured in this example. This was an example with Hadoop, but you would see similar ratios, not the absolute numbers, but ratios also in other systems. The actual work that is performed versus the overhead that you have for checkpointing, for building those camps, is fairly high, right? So that means the checkpointing overhead is so huge that you don't get a lot of work done. And it's clear that you should be able to do much better if you don't expect so many failures. And the problem is we are running the systems like Spark, Hadoop, or whatever. We're running the systems very often, not in an environment with tens of thousands of machines. Of course, Google, Facebook, and so on do that, but many others don't, where you don't have that many failures, right? And then you could be much more efficient. And the problem is, as I said, so you have to replicate those checkpoints to the machines, and this overhead is incurred all the time, even if no failures happen. And what we thought about is, can we avoid this overhead in failure-free cases? So how can we actually do better? And this is exactly the strategy of Optimus. And we call this optimistic recovery. And the observation, as said, is that many of those data mining or machine learning algorithms, fixed point algorithms, and now if you contrast that, so the failure-free execution, so I'm trying to get to my fixed point, right? I'm kind of doing solving some optimization or minimization problem here. And I have those plateaus which get me forward with each iteration. I'm trying to get to this minimum here, maybe. So each iteration gets me forward here. It's in the failure-free case. If I have a failure, that means maybe I crash here. Then if I have stored my state here, I can go back here and I can continue. This is the pessimistic recovery. Now, what optimistic recovery does, what essentially Optimus does, is when I have a crash, when I have a variant attack here, I have to walk and find a new road. So this is what I call compensation. And so this means I have to find a different point because what happens is, you have to remember, I lost part of my state. So I have a distributed state, and I've lost a certain amount of the state. So, and I have to somehow recover that state that I haven't stored. I get into that, how you do that in a second. But if I somehow recover that state, it may not be exactly the same place, but I'm somewhere there, and then I can continue. And now the question is, how do you recover if you have not stored anything, right? So that's the challenge here. And the interesting observation is, you can do this with what I call a compensation function that in the case of a failure can restore the state, but it's algorithm specific. And so you have to look at your algorithm. And so, for example, one very common machine learning algorithm that you may know of is entropy maximization, right? So which means essentially I want to maximize the entropy of a distribution where I know some things and some other things I don't. And if that was the problem you're trying to solve, usually one solves that by having a set of Lagrange multipliers that are distributed. So you're solving this through optimization or an iterative algorithm that iterates over a set of Lagrange multipliers. So it's called iterative scaling. It's an algorithm that was invented by Derek and Radcliffe. And this algorithm essentially I have a set of Lagrange multipliers, and in each iteration, I update those Lagrange multipliers. And I do so until I reach my fixed point. And now what happens if I do this in a large data set in a distributed setting, there are some Lagrange multipliers in each machine, and there's one machine maybe that crashes, and I lost all the Lagrange multipliers. So what do I have to do in this case? The compensation function is just set your Lagrange multipliers to an arbitrary random value. 42 might be a good number, or 17, and then continue. And you are guaranteed to converge. So you will be somewhere, but you are guaranteed to converge and you will arrive at the solution. So this is because of the property of this algorithm. Now, if we talk about PageRank, PageRank is another one of those algorithms, right, that you might want to execute. So how is it with PageRank? So in PageRank, what you have, you probably know PageRank, right? So essentially what you're iterating over and optimizing is you have this probability vector, right, for the visit of the pages. So you have this distributed probability vector. And if a machine crashes, you lose parts of this probability vector. And now what do you have to do? So when you crash, you have to actually invent new numbers such that the overall numbers that you have, this overall vector, is still a probability, meaning that the numbers that you know plus the state that you lost together has to sum up to 1. So invent all your numbers such that the numbers that you know plus the other ones sum up to 1. And then you can continue. That would be a compensation function here. And similarly, you can find compensation functions for other algorithms like ALS and others. And we have a couple of papers that you see here that actually describe that in more detail, and also would give you the math in more detail on that. But the key idea is always, so you can come up with those compensation functions, they're algorithm specific, and this is really like finding the next Roman road. Now, of course, if you remember, I said there's an assumption that has to be true. Remember, there was all roads lead to Rome is an assumption. So what is the assumption that has to hold here? Can anybody tell me what's the assumption that has to hold so that this really works? Because there is also the assumption here, obviously.
The convex problem.
Exactly, very good. It has to be convex. And if it's convex, it will hold. So the interesting thing is, though, so I had a discussion with some people at Facebook at some time when I presented that, and they told me that, okay, this is still interesting even otherwise if it's not convex, because of course you would then end up in a different minimum, but of course you would never know that it was a different one anyways, right? So they would be ready even to accept that, or it sounded like there's some people there even in that case, which I actually was not expecting. So with that, I will actually would like to conclude the presentation in the sense of saying and give you an outlook on the more on the current work that we are doing that is informed on this, and because I'm trying to put everything into a bigger picture here today. So if you look at big data platforms, right, we had the first generation, which is data warehouses and relational data management systems. The second generation that has scale out, that was Hadoop with user-defined functions. Third generation, you could say, is giving in-memory performance in the better programming model. There was Spark. The fourth generation, you had declarativity, you deal with iterative algorithms, that's Flink. And now the question is, of course, what's next, right? And what I'm betting on and what I've embarked on with my team, so building a system like Flink obviously is a large effort, I should say. So we did that over many, many years and with many students, right? So this is not something you depart from so quickly. But now with a new generation of students, we're looking at the next generation of systems. And there you, of course, always do some bets. And we are having two, currently I'm looking at two major projects. And that's also what Emmanuel already mentioned, that is Nebula Stream and Agora. And Nebula Stream, so the idea is, what are the new challenges? And the new challenges that I see in the next generation is that we have not a homogeneous compute cluster. So in systems like Flink, Spark, or whatever, our assumption is on the hardware level, everything is really a cloud-based cluster where you have lots of similar computers. And I think, and then that's what we're designing our system for now, which is really a data management system for heterogeneous hardware, or you could also say for the Internet of Things or industrial internet or smart cities or those kinds of environments, is a system where you have different hardware devices with very different capabilities. So there may be some that are just small sensors, there may be also some big clusters in there and others, and the system has to actually scale dynamically across all of those. And some of the code of the system runs on Raspberry Pis, some of it may run on a big cluster, right? And the system has to distribute your queries and your analysis workflows, which are, again, higher order functions. So it's not relational algebra, right? It has to distribute it in this very heterogeneous environment. And at the same time, in such an environment, you do not have, like in the context of Flink or Spark or so, we assume we have 10, 20, maybe 50 data sources at most that we would combine, right? But of course, if we talk about such an environment, we have sensors and we have millions of sensors. So we have potentially millions of sources, and we have a huge amount of standing queries that share results, right? So that means in such an environment, the research challenges that you look into are, I have constant evolution of the system because there's new nodes coming in, there's nodes going away. At the same time, I have a large amount of standing queries that are always there. And when I bring in new queries into the system, I have to actually consider what's already there, and I have to re-optimize that. So I have a running graph of queries, and I have to bring in new queries accordingly. At the same time, I have to look at how can I do this efficiently for multiple languages, because also the language front end, right? One looks at nowadays in many machine and data science applications, right? They're looking at Python and other languages, but we have to be sure that we can efficiently compile from many of those languages into our data flow engine, right? So then, and that includes in particular also dealing with the impedance mismatch that you might have when transferring data, so you don't want to constantly change data formats because that would be too expensive, right? There's lots of little technical challenges, but all of those we are considering now, and I have currently a team of actually 3 postdocs and 6 PhD students that are working on that. We've been working on this for 2 years now already, and there's always those big systems projects, right? In the first 1 or 2 years, you don't publish so many papers, and the papers come afterwards, like in the Flink case as well. So we have, for Nebula Stream, so far we have published 1 paper, which is more of a vision paper at CIDR, and 1 more application-oriented paper. And now we just got accepted some papers on the more recent conferences this year, and with respect to hardware-targeted code generation and the variety of aspects. And this is now emerging, but the system, and that's what I'm quite happy and proud of, we will within the next 2 weeks announce that we have this as an open source system available, Nebula Stream, and then we hope that others will also join, like with Flink, so we can build a larger community and can become a research platform for many. So this is one system that we are currently advancing quite a bit. And there's lots of exciting research to be done, and not just in my group, but in general. And the second thing that I'm currently looking at is, if you remember in the beginning, I talked about data being not the new oil, but the new soil. So essentially looking at a system, and they call this Agora, which is about, it's really a platform that allows to store, share, and share both data and algorithms and also compute resources, so that the idea is it's a distributed federated setup where people can register, I have this data stream or data source, or I have I have a particular algorithm that I want to share, or I have compute or resources that I want to bring into the system, and one can do so either for free or for pay, and there's various models. So it should support, in this case, both open and protected spaces where people can collaborate, and some kind of, I would call it almost like an app store, right? Where people can select data sources, can select algorithms that other people made available. And the system itself then can bring together data sources and algorithms. And there might be situations where there's multiple algorithms that solve the same problem, but they may have different quality metrics or different cost metrics, and then the system can, of course, optimize accordingly and decide which ones to choose, right? So that kind of setup. And the key thing is how to map this to a technical platform. There's a variety of challenges. So there we are currently looking at, for instance, one aspect is, of course, compliance. So you may have some rules, because if you're in such a federated setup and some data is in Germany, some is in the US, some is in China, with different rules on how to transfer data from one site to another, then you might have certain regulations that you have to be compliant with. And we had one paper that was just published at this last VLDB about compliant query processing, which I'm also quite proud of, because what we do there is we actually, you can define when it's permitted to ship data from one platform to another. We did this essentially using calcite, so in volcano style optimizer, and using traits, and you define, if you wish, what's permissible to be transferred, and if some masking functions are needed to transfer, so the anonymization, pseudonymization, like k-anonymity or so, and then the system can find, if you now write a query, this is now only relational algebra, though I should say, this is not our second order functional programming model, so far we've only done that for relational, but we hopefully can extend that soon. So for relational queries, you can specify a query, and you have all of those constraints, which data is legally to be shipped, let's say from China to Germany or whatever, or across organizational boundaries. And then the system will first check if it can find a compliant plan, and of course using also the traditional efficiency metrics that the query optimizer would use. And then the next step that we look at now is, if you cannot have a compliant plan, could you actually introduce new maskings or anonymizations operations so that you could make a non-compliant query compliant, right? So there's a couple of really interesting research challenges here. So this is one example. Another one that we're looking at there is how can you leverage modern hardware for that? So in this case, like trusted execution environments, so that if you're in a distributed setup where you do some computations, right, you need to make sure that in this case, you have some data, but you would not want to share the data or the computation, so that the party that does the computation doesn't see what they're computing on. And of course, Intel's TEE allows for that, right? The trusted execution environment, you have some hardware support for doing so. And we just had a paper that just got accepted also at VLDB that looks at exactly this, namely, how can I implement in this secure enclave of a TEE relational operations. So again, there we are, so in Agora, we are so far mostly looking at relational, although we eventually have to look at this richer set that I talked to you about in Flink, and that we're also using a nebula stream of operations and higher order functions. But so those are examples. And then of course, there's many other questions in that. So that means we have lots of research challenges that are in the area of big data processing, heterogeneous hardware and heterogeneous distributed environment. But we are also looking at a variety of other topics, and I think I'll save us that. And then just as a point, if any of you is graduating and is looking for a next step in academia, we actually are currently having positions open. And if you're interested in any of those topics, I'll be happy also to hear from you as well. But with that, I'm happy to conclude. And there's lots of more things one could talk about in our space of data management, big data, right? But I think I'll leave it at that for now, and I'll be happy to answer questions. Thank you.